Thanks all for being here. So if you don't hear us online, write something somewhere at some point. We are here to listen to Ossi Räisä presenting his work about statistical inference with differential private synthetic data. Antti Onkela will start by presenting briefly the work group of Ossi. Please. Yes.
Okay, thanks. So before we get to the actual topic, I wanted to briefly introduce the work we do on privacy-preserving machine learning and AI at FCAI. So this is our team, 2 postdocs, 5 doctoral researchers, and 2 PIs, plus a number of master's students. And very briefly, so the background of our work is that we are interested in privacy-enhancing technologies that can enable securing many uses of machine learning, including avoiding leakage of sensitive information through trained models, training models in a more privacy-preserving setting on distributed data using technologies like federated learning, and also what Ossi is going to be talking about today in anonymizing sensitive data to allow sharing it. And the common theoretical foundation for our work is differential privacy. And Ossi will tell more about the details. But this is a kind of technology that has been around for a little less than 20 years. And it's already been adopted by agencies like the US Census and most of big tech to ensure privacy in machine learning and in other cases of users cases as well. So in broad terms, our work is to develop methods to improve the utility of machine learning under differential privacy. And our work ranges, covers a broad range from some fundamental theory of differential privacy to deep learning, private federated learning, differential private Bayesian inference, as well as some applications. And a big current focus is on this using differential privacy to generate synthetic data, of which you'll hear more in this talk. And we're involved in a number of initiatives. One is on the Dataset project, which combines kind of the societal aspects of data use and privacy. And we are also part of the European Network of Excellence, European Lighthouse on Secure and Safe AI ELSA. But with that, I'll let Ossi start with the actual technical talk.
All right, so I'll start by introducing the topic. I think I have to apologize to the audience here because it looks like the projector is cutting out the part of the slides. So let's hope that's not too big of a problem. All right, so I'll start by introducing the synthetic data. So, well, basically, the idea here is that we would want to make data as widely available as possible because that's very beneficial to research in machine learning and many other areas. But this conflicts with the privacy of the data subjects when the data is sensitive, for example, like healthcare data. And synthetic data is a potential solution to this problem. The idea there is that you take some kind of generative model and train it with real data, and then sample synthetic data from the model so that your synthetic data looks just like the real data, but it doesn't have any records from real people. So it offers this compromise between the data or making the data available and privacy, because the records don't correspond to individual people, so the data is anonymized in some sense. But then the population level quantities in the data should be approximated by a generative model, so analyzing the data should be useful. But if the synthetic data is too accurate, or for example, if the generative model has memorized parts of the data, this can still compromise privacy. And differential privacy is this definition that quantifies the privacy loss from publishing the results of an algorithm. And we can apply it to synthetic data generation, which then ensures that releasing the synthetic data doesn't compromise privacy. But then we also need to be able to analyze the synthetic data. And well, because it looks like the real data, we could just run our analysis for the real data. But do we actually get useful results? If we want uncertainty estimates, something like confidence intervals or hypothesis tests, those are going to become overconfident if you just ignore the synthetic data generation. And that's because the synthetic data generation adds extra randomness to the process. And if you're ignoring that, then you become overconfident. And differential privacy makes this even worse because it requires adding some extra randomness, which you're then ignoring. Here we have this like very simple toy example, which shows this. So we generate some data with logistic regression. It has just 3 binary variables. Then we take one of these 4 DP algorithms and generate synthetic data with them. And we also test several values of epsilon, which quantifies the strength of the privacy guarantee. And once we have the synthetic data, we try to infer the coefficients in the logistic regression, and we compute confidence intervals for those. And because we're specifically computing 95% confidence intervals, so those intervals should contain the true parameter values 95% of the time. And the y-axis shows how often they actually contain the true parameter values. And you can see that none of the algorithms, or with none of the epsilons, get to 95%. So all of these results are overconfident. So next, I'll give some background on differential privacy. And then I'll be moving on to our solution to this problem. So as I said, differential privacy quantifies the privacy loss from releasing the results of some algorithm, which analyzes the data. And it's defined by this inequality, which requires that when you change a single person's data in the dataset, the probabilities of getting different outputs cannot change too much. And the too much is quantified by the epsilon and the delta over here in this inequality. And this can also be kind of interpreted as a success probability of inferring whether or which one of the data sets was used. So did we use this person's data or this other person's data? And one very useful property of DP is post-processing immunity. So any post-processing on the results of the algorithm cannot reduce the privacy bounds. So the way we actually get differential privacy in our work is called the Gaussian mechanism, which simply adds Gaussian noise to the output of some function. And we get an epsilon delta guarantee when we choose the variance of the noise appropriately. I won't show what the actual formula for that is, but it depends on this sensitivity of the function, which is just how much the value can change when you change one of the data points. So next I'll go into our solution, which is called noise over multiple imputation. So multiple imputation was originally developed to deal with this uncertainty problem in the context of imputing missing data. And then later on, it was adapted for synthetic data. And the idea there is that you generate multiple synthetic data sets, then you analyze all of those, and then combine the results with these rules called Rubin's rules. And because you get the multiple results from the analyzing each synthetic data set, you can use those to account for the extra uncertainty in the synthetic data generation. And you need to sample the synthetic data sets from a posterior predictive distribution so that the combining rules actually work. And with differential privacy, this becomes very tricky, because then the posterior has to take the noise you add for differential privacy into account. So over here, we have the S tilde conditioning the posterior predictive instead of the real data set. And the S tilde is a noisy summary of the data. And this means that the posterior predictive here has to actually contain the noise model for the S tilde. And I'll briefly go over Rubin's rules. So they combine the results from each analysis of the different synthetic data sets. And the inputs are just point estimates and variance estimates from the analysis. And then the outputs are the parameters of a t distribution you can use to compute confidence intervals or hypothesis tests. And here's the point estimate is the Q over here. And then the variance estimate is either one of these. The t can have negative values, so you can correct those using this. And then here's how you get the degrees of freedom for the t distribution. But I won't go into more detail on those because we don't have the time for that. So next I'll go into how we actually need to generate the synthetic data to be able to sample it from the noise-aware posterior predictive. So there is some previous work on this. For example, there's this algorithm by Bernstein and Scheller, which does noise-aware Bayesian inference, but they only, their algorithm really only applies to like very simple exponential family models. And we generalize their framework to more complex models, which you could actually use for some realistic data sets. So the general idea is to just focus on discrete data and summarize that with marginal queries. I'll go into those a bit later. Then we just use the Gaussian mechanism to add the noise to get dp. And then we infer the posterior for a Bayesian model, which includes this Gaussian noise. And then we sample the posterior predictive to get the synthetic data. And we're calling this algorithm noise-aware private synthetic data using marginal queries, or NAPSU-MQ for short. And because we have post-processing immunity, we could technically publish the query values, and everything after that is also DP. So we can generate an arbitrary number of synthetic data sets, and it doesn't change the previous bounds at all. So then I'll briefly go over marginal queries. So they simply count the number of rows with given values for given variables. So for example, in this table, we could check if age is between 30 and 39 and income is not over $50,000. And then on the example table, there's 2 rows with this. And with just these marginals, we won't get very far. So we'll look into full sets of marginals, which is just all of the marginal queries for some variables. And over here, if you look at the full set of age and income, you have 2 values of age and 2 for income, so it gets 4 queries. And you can also have more than 2 variables or just 1 variable. And for the Gaussian mechanism, we need the sensitivity of these. For a single marginal, that's pretty easy because when 1 row changes, the value can change it by just 1. But when you get a full set of marginals, there's actually just 2 values that can change in the whole full set, no matter how many queries it actually contains. So the sensitivity actually depends only on the number of full sets of marginals you have. All right, so then to the Bayesian model. Here are the variables we have in the model. So first there's the model parameters theta. Then there's the real data x. And the queries, or the marginal query values s, and then the noisy marginal query values s tilde. And then there's also this hypothetical data set, x star, which is in the posterior predictive distribution, which is shown over here and cut off by the projector. Right, so then we need to model how the data is generated from the parameters theta. So we do this with these 3 constraints. First, we want that the marginal query values have the correct expected values. Then we want that each data point to be IID. And then we want the distribution to have maximal entropy. And this gives this exponential family distribution, which we just call maximum entropy distribution. And this also turns out to be a Markov network, which will be useful later. So now we can write the Bayesian model. So we have the parameters with their prior, then the data from the maximum entropy distribution, and then the marginal queries, and then the noisy marginal queries. And now to actually sample the posterior over here, we need to somehow get rid of S, because it's a fairly complex discrete variable. And we can do this by first doing a normal approximation on S. And this works because it's a sum over all the data points. So it has approximately a Gaussian distribution by the central limit theorem. And now you get the mean and the covariance of the query values in the normal approximation. And then, because there were just the two Gaussians over there, so now we can just marginalize out S, and we're just left with this. And this is something we can actually sample with standard Bayesian inference methods. The ones we use are the Laplace approximation and the no U-turn sampler. And we also need to set a prior, which we just choose to be a standard Gaussian with a fairly large standard deviation, which is kind of a non-informative prior, but you can also choose, you could choose other priors. And we still need to actually compute the mean and covariance for the normal approximation. And because the maximum entropy distribution is an exponential family, you can compute them from these derivatives of theta 0, which is the log normalizing constant of the maximum entropy distribution. And you can compute theta 0 by using the Markov network structures and the algorithms developed for that. The one we are using is called variable elimination. And this is like computationally feasible when you don't have too many overlapping or like too many marginal queries with overlapping variables. Because otherwise, like the complexity is going to grow exponentially in the number of variables you have. And the derivatives we have can just be computed with automatic differentiation. Then we just have one more problem we need to deal with. So if the queries have linear dependencies, the maximum entropy distribution won't be identifiable. And with this will make the no U-turn sampler pretty slow. But we can make the queries identifiable by using this canonical parameterization from the graphical model theory. So we can use this parameterization to find a subset of the queries without linear dependencies, but which still has all the information that the full set of queries had. And then after we drop, or after we just keep those queries, then we have this, or we have a set of queries without linear dependencies, and then we have an identifiable model. All right, so then I'll go into some results. So this is the toy data example, but now we also have our method in the blue. And also we have our method with, or the NA+MI method with another synthetic data generation algorithm, which is called PrevalCM. And recall that the coverage was how often the confidence interval contained the true parameter values. And these are 95% confidence intervals, so the coverage should be at 95%. And our algorithm is basically at the 95% every single time. The other algorithms, except PrevalCM, are not there. And then PrevalCM is usually above the 95%. So it's actually like basically 100%. So it's very underconfident. And then we have results from the adult data set. Now the top row has, again, the coverages, but this time for different confidence levels. And having this like confidence level coverage plot means that you want to be as close to the diagonal as possible, because you want the coverage to be close to the confidence level. And our algorithm is pretty much there. Then we also have this other algorithm called PGM repeat, which just splits the privacy budget into m parts and then repeats PGM m times and then uses the Rubin's rules for the multiple synthetic data sets you get that way, which is kind of this like naive baseline way to get multiple synthetic data sets. And it doesn't like technically meet the assumptions of Rubin's rules, which is probably why it's actually very underconfident. And then on the bottom, we have the ratio of the synthetic data confidence interval width and the real data confidence interval width. And the black line there shows, or is at 1, so it's at where the synthetic data intervals have the same width as the real data intervals we have. So you can see there that our method generates somewhat wider intervals, and especially with the smaller epsilons generates like several times wider intervals. But then that's going to be the price of like actually having accurate confidence intervals. And then here's the same plots for this much larger US Census 1999 data set. Here the PGM actually works pretty well for the larger epsilons, probably because the data set is much larger. And then here's some results on the accuracy of all the possible marginal queries on either one or two-way marginals, like on the synthetic data. And you can see here that NAPSU-MQ is very close to PGM on like all the epsilons, except maybe epsilon 0.1, where it's like pretty close, but not almost there. And this is on the adult data set. And then here's the same on the US Census data set, which has very similar results. All right, so then to limitations. So, well, first of all, NAPSU-MQ is limited to just marginal queries on discrete data, but we can discretize continuous data. So this might not be that big of a limitation. And then, of course, the general framework, NA+MI, is not limited to having just NAPSU-MQ. If we could develop like other noise-aware generation algorithms in the future. But the bigger limitation is that the selected queries in NAPSU-MQ have to actually contain the relevant information for the downstream analysis. Otherwise, the confidence intervals could still be overconfident. And this basically means that either the synthetic data provider has to know a lot about the analysis, or they have to pick a lot of marginal queries. But if they pick a lot of the queries, then as I said earlier, the computational complexity is going to be exponential in the number of variables. And even if they don't pick that many queries, this is still very computationally expensive. So to conclude, estimating uncertainties from synthetic data requires accounting for the extra randomness in the synthetic data generation. And we can do this under differential privacy with our framework NA+MI and the data generation algorithm NAPSU-MQ. And our experiments show that this gives accurate uncertainty estimates. And the full paper for this work was published at AI Stats with the same title as the talk. And we also have an implementation available in the TwinPy library, which also contains some other tools for DB synthetic data generation. All right, that's everything. Thanks for listening.
Are there some questions from the room? Are there some questions from online? Maybe while there are the people online like that question. So at some point, I mean, I don't know if you discussed that, but you chose the priors that is normal with the standard deviation of 10. Is there a reason for that?
No particular reason. It's simply a standard kind of non-informative prior?
I mean, non-informative.
Well, it has a large variance.
Yeah.
Meaning that.
Yeah. Okay. Yeah, makes sense. And here, so we use two different methods. So you have a reason to prepare one or the other because this is kind of normal. You would expect that that's approximation for far better. So why using that?
Yeah, so the loss of approximation is much faster of the two. But in cases where the queries have small values, it doesn't work that well because then the posterior is not exactly Gaussian. And the adult example over here is one where we actually had the small curve values.
Okay.
So here we actually had to use the no U-turn sampler.
Okay.
On the toy dataset, we just used the Laplace approximation, and that works very well.
And so if you have to change, so you would recommend in general to use. So I mean, using a Gaussian prior allows you to have a Laplace approximation that also works well if you have a good reason to choose it. But if you had to go away from this kind of priors, would you have like other recommendation or always use another informative one? Or?
I think one prior, interesting prior might be the conjugate prior for the maximum entropy distribution, which is probably a bit more computationally expensive because you have to compute the theta zero for that prior, if I recall correctly.
Yeah. Yes.
But it might give you a bit more interpretable prior.
Yeah. So no question from the room, it seems. No problem now. So I think we can thank you again, Ossi and Andy for the introduction. Thanks a lot.